Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here. Hit the notification bell. You'll get notifications for this series and a bunch of others on our channel. We're doing multivariable calculus. We're in chapter 2, which is double and triple integrals. Section 2.6 specifically is triple integrals now. And we are going to this lecture do triple integrals over rectangular boxes and Fubini's theorem for triple integrals. Specifically, notice that we're going to have a whole bunch of Fubini's theorem says for functions of two variables you can do dy dx or dx dy. There's two permutations of two objects. Now there's 6 permutations of dx dy dz. So the ones that start with x dx, the ones that start with dy, and the ones that start with dz. Fubini's theorem is going to have 6 iterations you can compute anyway, and they all calculate the same number. A gun and a rope and enough stuff to hang yourself, for sure. Alright, triple integrals over rectangular boxes. We're going to do the exact same thing. We tried to mimic Riemann sums for double integrals, and now we're going to do the same idea, except now we have a function which is of 3 variables, so that surface is now a hypersurface in 4 space, which I can no longer draw or imagine very well for myself. Possibly using shadows and projections, but well, that's a game for a different video and a different day. We're going to take a box AB cross CD cross EF. In our 3 dimensions, this is always the x direction, this is the y, so this was A to B, and C to D, and E to F. Get it right. That's what we're doing. You chop the box into a bunch of subcubes, and then what we're going to do is, in each of those sub-boxes I, J, K, we're going to have a volume now, delta V, which is delta x times delta y times delta z. Over that region, we are going to sum all of those things up, so the approximate volume or hypervolume over that would be the sum of all of these guys, f of xi star, or xi, yi, zi, times dv. And if we take the limit of that and chop it up finer and finer, just like we did with double integrals, we get the definition of a triple integral of our function w over a rectangular box is the limit of this if it exists. First of all, for Fubini's theorem, we're going to have 6 choices of rearranging them all, and we can have starting with dx or dy or dz and all the possible combinations. And then what we're going to do is, the last time we had 2 general types of regions, whether we express the functions of x or y as functions of x, or x as functions of y. This time we're going to have 3 cases. We can have the regular z as a function of x and y, or now we can have x as a function of y and z, or we can have y as a function of x and z, and you're going to want to stick to, and I'll try to stick to it first, especially when we explain the regular z as a function of x and y, and I don't know why they changed, but sometimes when we do complicated regions in 3 dimensions, it's easier to phrase them in terms of the other functions. Let's do some of that. Fubini's theorem for triple integrals. You have to make sure, basically this is one of the major tour de forces even in single variable calculus. We say that on any closed interval we have that if a function is continuous on that interval, then the antiderivative, it's always integrable, the antiderivative exists on that interval, and you can compute it using the fundamental theorem of calculus if you know what the antiderivative is. And that's the problem. Even in 1 dimension, the theorem says if your function is continuous, it has an antiderivative on intervals. It does not tell you how to compute them. You're on your own. What this is saying is the same thing in 3 dimensions. If you have that your function of 3 variables is continuous over a rectangular box, that integral does exist. It says that limit exists. It does is what they're saying. And you can compute it as this iterated integral. And notice that they didn't do in the book again, which I copied down. But if I was going to copy it down the right way, what it's saying is we started with dy dx and always did y first, the inside one, because we're writing y equals, or we had a function z equals f of xy, and then we picked y first and then x always. Now we have w is f of x, y, z, so shouldn't I be picking z first, then y, then x? They've written it like this, but the whole point is, yes, we can do all of those. Fubini's theorem is telling us now that I can also write this as the integral from a to b, the integral from c to d, the integral from e to f of x, y, z, dz, dy, dx if I want. And then how many are there? Those 3 items, and I can rearrange them in any order. There is 3 factorial, which is 6 ways of doing this, permutations of 3 objects, and I'm going to get dx, dy, dz I could use, or I could use dx and then permute those guys, dz, dy, or we could have start with y, dy, dx, dz, or dy, dz, dx, or we could have dz, dx, dy, and dz, dy, dx. which is the one I tried to write right there. This is what Fubini's theorem is saying. If it's a box and your function is continuous, use any one of these to compute any order you want. I like to do this one because it's the similar to doing the y then the x, and this is going to be able to phrase your function as z equals f of x, y in a lot of cases, instead of the other ways that we're going to find the bounds for the region when we put them in here, is what I'm saying. We're going to have to get a z1 to put into here and a z2. If you phrase it this way and do z dy dx first, this is always going to say you can do the regular, where we've done this for the whole part of the course, as phrasing z as functions of x and y. If you change these, you're going to have to say x is a function of x will be a function of z and y now, and it's going to be weird for you at first. So this one is what I pick for Fubini's. Let's do an example. All right, it wants us to find the triple integral of w, which is xz squared, over the box B, which is 0, 2 cross 1, 6 cross 3, 4. If you really want, the x goes from 0 to 2. It's saying the y is going to go from there, and then the coordinate axis will be slightly over there, but we have a box that we're going over. And we're integrating around, and then we have coordinate system somewhere, ... Draw your picture, you should. And that says we're going from, x is going from 0 to 2, and then this one is going from, y is going from 1 to 6, and z is going from 3 to 4. So your coordinates are over there somewhere. Once I do that, I see, because it's Fubini's, again, we're going to have to start trying this when we have 3 types of general objects of type 1, where we have the functions z equals f of x, y, and the other 2 scenarios. And that's going to get crazy in the other videos. For now, it's a box. So what do? Fubini says that the triple integral over this box of my function xz squared dv is now equal to the integral from, and I'm going to use this order specifically, so x on the outside, 0 to 2, then y in the middle, 1 to 6, then z, which is 3 to 4, and that's going to give me x z squared dz dy dx. And remember, I'm prepping because I have experience, and when we switch from rectangular boxes to, holy crap, trying to get 3 types of general regions of objects in 3 space to integrate over, you're going to want to try and phrase, if possible, z equals f of x, y, and not the other 2 where we have f of x, y, z, or y is a function of x and z. We're going to want to stick to this one because that's what we phrased everything as, but you have to have the dx, dz first so that I can put those in there, z equals f of x, y, when we integrate more difficult ones. That was a slight tangent, pun intended. What we're going to do here now is I'm holding x and y constants, I'm integrating z, so this is going to give me the integral from 0 to 2, the integral from 1 to 6 of x over 3 z cubed evaluated from 3 to 4 dy dx. What that gives me is the integral from 0 to 2, the integral from 1 to 6 of x over 3 times 4 cubed minus 3 cubed dy dx. That gives me the integral from 0 to 2, the integral from 1 to 6 of x over 3 times 64 minus 27, which gives me 37 dy dx. This gives me equals 37 over 3, the integral from 0 to 2 of x, y, evaluated from 1 to 6 dx. Now I put those in there, that's going to equal 37 over 3 times x, and then we're going to get 6 minus 1, and then this is the integral from 0 to 2, of dx. Who are you saying sorry to? My brain, it won't listen. Equals, this is 37 times 5, 35, 15, 16, 185, so I'm going to get 185 over 3, the integral from 0 to 2 of x, so that's going to give me, by the fundamental calculus, I could take the antiderivative, that's going to give me 1/2 x squared evaluated from 0 to 2, which is going to give me 185. I get 2, which is 2 squared, 4 over 2, which is 2, times 2 over 3, which is 185. You can double it, it doesn't matter. Don't be shy to do this. 0, I get 10. And then I got 16, 17, and then I got what? 3. This is 370 over 3. Please subscribe right here, hit the notification bell. You'll get notifications for this series and a bunch of other ones. Next time what we're going to do is more integrals using Fubini's theorem over boxes. Then we're going to do general regions of all 3 kinds.